Welcome back, boys and girls, to another lesson in Algebra 1. Today we're going to talk about exponential growth and all of its wonderful applications. But first, before we get into that, let's talk about something called function notation. Now, Mr. Sullivan introduced you this a little bit, and Mr. Kelly is going to go much more in depth in the next unit, but I want to make sure we have at least a quick little understanding of some things basic. So here we have, write out this, 3x plus 4. If we have an equation of this line, y equals 3x plus 4, writing it in function notation would be just replacing the y with f of x. That simple. So then it becomes f of x equals 3x plus 4. That's all it is. We take the y and replace it with f of x. Now when I say f of x, I'm including a little word of in there. It does not mean f times x when you see this. It's not f parentheses times x, it's f of x. So instead it allows us to describe what we're going to plug into the equation. So here's what I mean by that. F of 2. What in the world does that mean? It means we substitute in the number 2. So it looks like this. 2 goes into x, so it's 3 times 2 plus 4. 6 plus 4 gives us 10. So f of 2 equals 10. That just means if x equals 2, then y equals 10. That's all this means. If x equals 2, then y equals 10. So here, I'm not going to go through plugging it all in, but if we have f of 5, then we'd get f of 5 equals 19. I already did this one out. So I know that it equals 19. So again, that just means that x equals 5 and y equals 19. Or in other words, we could write a coordinate point of 5 comma 19. That is function notation. So when you see this little thing like this, or an f of x just means y, but when you have a number plugged in here, it's really nice because it tells you what number you're plugging in, and it's a coordinate point. Okay, Mr. Kelly will cover that much more in depth in the next unit, but we're going to use some of that in this lesson. So applications of exponential growth. It is amazing how many times our students will say, Mr. Bean, I'm never going to use this. Okay, well, for some of the stuff, honestly, that's true. But there are a lot of people that use a lot of different mathematics all over the place. So exponential growth, you'd see this everywhere. It's in microorganisms and in viruses. It shows up with human population growth. That's exponential growth. If you have some type of nuclear chain reaction, if you've got, a lot of times economic growth can be considered exponential growth, well, depending on the year. And a Ponzi scheme, oh yeah, this is bad stuff. Like people who scam you and get money from you, and it's complicated. You don't have to read that whole thing. But if you know what a Ponzi scheme is, that can be exponential growth. And processing power of computers, those things. In fact, I really like this one because this is my very first gaming system, Nintendo ES. And look at that. It's almost exactly the same power, CPU speed, the RAM. Has the Apollo guidance computer from the 1960s? Apollo was, yeah, 1960s. So you can see all of this stuff, exponential growth, has a lot of applications that we can use this in. So to start off, let's talk a little bit about some things that Mr. Sullivan taught us in the last unit. So I have here my first graph. Let's graph this 3x plus 1. I'm going to go ahead and give you the dots. Okay, there's my dots for 3x plus 1, and then we could graph it. I probably should use a line so I can do this straight. And there's a straight line, so include that on there. So what is the change in y value for every x? Every time we move over an x, our y value is adding 3 each time. We are adding 3 to the y value. Adding 3 to the y value. Well, what about the next one? Okay, so let me give you some points for this one. So this graph you can see is the red dots. It's going to start at the same place at 0, 1 as the line did, but then it doesn't start off as fast, but then it passes it. It goes much faster, and it's going to grow steeper and steeper. So what is the change in y value? Oh, I guess I could draw a line kind of. Oh, this is awful. Try and draw a line that kind of connects those curves there. Oh, okay, sorry. So what is the change in y value for every x? In this case, we are multiplying by 3 each time. Multiply 3 to the y value. So what this is, if you remember what Mr. Sullivan taught us, was that this was arithmetic, an arithmetic sequence, and this one was a geometric sequence. Well, in other words, this is exponential growth. That's what, oh, I did that wrong. This one is exponential growth. And then this one's the linear growth, which is what we've been doing in a lot of our stuff so far this year. So linear growth and exponential growth. And the difference is this has a constant change here, if we're just adding 3 each time, whereas this one we're multiplying by 3. Okay, the next thing we're going to do is identify if a function or an equation is linear, exponential, or neither of those two things. Okay, so that's the only 3 things we're trying to say in the practice today is it linear, exponential, or neither. So how do we tell that? Well, the linear ones, let's jump and look and see if we can recognize the linear. This one right here, when you have, this is like your slope. If you can see something that looks like it's the number times the variable, that is your slope. And so this one is linear. But these are different. These have exponents. So which one is exponential? If they've got exponents, there's a good chance one of them is exponential. So which one is it? Let me give you a hint. Here's how I remember it. If you have exponential and you take the x out of exponential, so in other words, here's an x and it's in the exponent. If you take the x out, you just have exponential. That's not an exponential function. That's an exponential function. Okay, there's no such thing really. So the x has to be in the exponent. In other words, the variable is in the exponent for it to be exponential. So this one's your exponential. Exponential. And then this is the one, yes, you do have an exponent, but the x is not in the exponent, or in other words, the variable. In this case, it's an n. So this one's just neither. It's neither exponential, nor is it linear. Neither. Okay, so that's how you do those. Now on to what's called standard form. Extremely important. We have a times b to the x. What this number here in front, it represents the initial value, how much we're starting with. It's the very, very beginning value amount. And this is how much it's going to grow by. It's called the growth factor, what we're multiplying the initial amount by each time. Okay, so get that written down. Pause here if you don't have that written out. The first thing we're going to do is make sure we understand how to graph these. Real simple. We're just going to use a few points. Let's just plug in an x equals 0, an x equals 1, and an x equals 2. Those are usually the easiest points to do, 0, 1, and 2. If I plug in a 0 to this, I'm going to have 2 times 4 to the 0. Now, you can't do 2 times 4 and get 8 because you have to use exponents first. So 2 times, what's 4 to the 0? 4 to the 0 is 1. Anything to the 0 power, you're going to get a 1. So then this is 2 times 1. It is a 2. So if I plug in a 0, I'm going to get a 2. Now let's try the 1. If I do 2 times 4 to the first power, so I'm just plugging a 1 in here, then I get 2 times 4 is 8. And then let's do one more. 2 times 4, so 2 times 4 raised to the second power this time. I'm plugging in a 2. Well, that's 16. 2 times 16 is 32. All right, so here's some coordinate points we can use. Let's graph this. 0, 2, here's 1 point. 1, 8. Whoa, 1, 2, 3, 4, 5, 6, 7, 8. And then 232 is way, way, way off the grid, way up here. So we're not going to graph that point. And then, so if we were graphing this, it's just really steep, but we want to make it curved. It's not a straight line. It's curving. And then if you were to go off here to the left, it would start to flatten out over here. Okay, so that is what this graph looks like. All right, so when you're graphing these on your own, all you need, you can take a calculator, just get a few points. I would recommend you just go 0, 1, and 2. Those are the easiest. You plug them in, get a few y values, and then there you go. So let's do this one. This, again, you would have to use a calculator, okay, because you're going to go, I'm going to give you actually several points to help us out on this. So let me pause here and you can write these down. Look at these crazy numbers. The way I did this, again, is I plugged in a 0 and I just took a calculator and did 0.6 times 1.5 to the 0. So that's just 0.6. That one's easy. But then all the others, I had to keep multiplying by 1.5, 1.5 over and over again. The reason I did this so many times is because I could fit all of these on my graph. There is no way I can graph a perfect 0.6, let alone a 1.35. So this is what you do. You just kind of eyeball it. We're trying to get a decent sketch. So this is about 0.6. And then 1, about 0.9, somewhere around there. 2 is 1.35. Again, you're just trying to get a little bit of a feel for where this is. 3, and it's just barely above 2. 4 is barely above 3, so it's basically 3. 5 is 4.5, and then 6.83, way up there, almost to 7. Okay, So now you can kind of see what's going on. This is a really nice graph of exponential growth. It starts off just barely growing slowly, and then it's starting to take off here. So, and then if I had a pencil, I could probably do this a little bit better than with my marker. And there you go. All right, so you're going to use a calculator to help you get these points, and then you plot those points on your graph. Next up, if we have a table of values, instead of using the calculator to do a regression line like we used to practice with some of Mr. Bruss lessons, he taught us how to use regressions on a calculator. I'm telling you, this is going to be an exponential function. Later on in this unit, we're going to have to distinguish between exponential and linear, but you've kind of already done that. So basically, what am I multiplying by to get from here to here? Okay, whatever I'm multiplying by. So here's my equation. Y equals, what's my initial amount? I'm starting with a 2. If x is 0, then that's my initial amount. Okay, x has to be a 0, though, for this to work. And then I'm going to have something raised to the x. All right, and that something is whatever I'm multiplying by to get to each one. Well, if I don't know what I'm multiplying by, let's just use my calculator from my computer here. So if I don't know what I'm multiplying by, then I just go the other way. I divide, start at 5.2 and go that way. Oh, what happened to my marker? 5.2 divided by 2 is equal to 2.6. Let's try another one. Let's just see if it works. 13.52. Let's go 13.52 divided by 5.2 equals 2.6. All right, so that is my exponential growth. So we put right here 2.6 because that is my growth factor. It's how much I'm multiplying 2 by 2.6, and then every number after that, just like a geometric sequence. We just keep multiplying by 2.6. So that right there is the equation that fits for these coordinate points. Next up, we're going to talk about percent increase. For some reason, this is a struggle for a lot of kids, so let's try to make this as easy as possible. We're going to start off with some A, amount. So this is our initial amount, A, kind of like what we've talked about before, and it's going to be growing by a certain percent. So this right here, this percent increase, is going to be kind of like an R. It's an interest rate. So in other words, I could have written this as 1 plus R, 1 plus a percent, or a rate at which it's increasing. So I'll refer to this letter R, but it just basically means the rate at which it's increasing, or in other words, the percent. But we always have to convert it to decimals. So get this written down. That might be a little confusing. I'm going to show you with some examples how this all works out. So let's do our first problem. So we have $100. So we're trying to create an equation here. So let's go, I have $100. I'm going to have y equals, my initial amount is 100. And now I'm going to do 1 plus the rate. So I'm just going to say R, the percent increase, and then raised to the x. So let me go back to this. This 1 plus percent increase is your B. That whole thing added together is the A and then the B. So if I write here, y equals 100. So I'm going to say 1 plus, now what's the percent? It's 23% raised to the x. But you can't do percents for this because remember on our notes it says we have to convert to a decimal. So then I'm going to say y equals 100 times 1 plus 0.23. How did I get 0.23? You move the decimal twice. Remember, from converting between percents and decimals, you just move the decimal 2 times over. So now it's a 0.23. And then my final answer, I need to add those together. Y equals 100, 1.23 raised to the x. And that is my final answer. After you actually need to add these together and get your B. Your base or your growth factor is a 1.23. Interestingly, that some kids you're watching this right now thinking, oh my gosh, Mr. Bean, this is so easy. Why did you do all those steps just to show 1.23? Well, there is a reason behind that. Mainly because when we get to the next lesson, there's going to be some things that are a little bit confusing with this, and I want you to get used to practicing how you just start with the number 1 and then you're adding something to it. So let's do this again. Here we're going to start off with y equals, our initial amount is 200,000, and we are doing a 1 plus my percent increase. So I'm going to skip writing the R here. Here we're just going to write a 1.5, but oops, that's sloppy, 1.5, but I need to include the percent there so that I know, don't add this together yet. Because this tells me when I have a percent, I'm not done, raised to the x, until I convert it to a decimal. So y equals 200,000. And then it's times 1 plus, now move the decimal 2 times. So if it's right here and I move it 2 times, let's put some zeros in front of this so you can see it. 1, 2. So let's come back down here. It's going to be 0.015 raised to the x. 0.015 is 1.5%. So final answer, y equals 200,000. And then my growth factor, the b here, is 1 plus this. So it's just 1.015 raised to the x. Again, some of you probably can do this in your head with hardly doing any of this work. That's good, but I want you to actually write 1 plus. Show that in your work. It's very important for understanding what we'll do next in the next lesson. All right, go ahead and pause the video now. Try this one on your own. I'll have the answer up here in just a minute. And there's your answer. You should have 150 times 3.05 raised to the x. And the 205%, move the decimal twice, it becomes 2.05. And then if you're starting with 1 and adding, that's where the 2.05 comes, or the 3.05 comes from. Okay, good. So there's our word problems, how we set these up. Now let's work the other way. Let's go backwards. If we start off with initial value, this isn't too bad. Our initial value is 6 here. Our initial value on this one, -8. That's the easy part. Okay, but now here's where it gets a little bit weird for kids, and that is, I'm going to write this out here. We need to write, and I didn't leave you a lot of room, so kind of squeeze this in. 1 plus the r equals 1.516. Now let's see what I'm talking about here. This b, the base of this exponent, is 1 plus r. And if we know that it equals 1.516, we're just trying to figure out what r equals. So if you solve for r by subtracting 1 from both sides, you'd get a 0.516. So that's my r. And then if I want to say what the percent is, you just move the decimal twice. So the answer is 51.6%. Just like that. Okay, so you set it up first, solve for r, then you know what the r is, convert it to a fraction. Okay, so let's try this one. We're going to set up that we know that 1 plus the r is going to equal 3.2. So if we know that, now let's solve for r. We subtract 1 from both sides and get 2.2. And so if that's my percent, or that's my rate at which I'm increasing, we've got to figure out what the percent is. So again, you move the decimal twice this direction now, 2 times to the right. I'll just go ahead and add on an extra 0 here at the end, move the decimal 2 times, and then you have 220% increase. Okay, so follow these steps carefully. I know this seems really easy for some of you, but please follow these steps. It'll make it so much better when we get into the next lesson in 7.2. And I think that's the last problem, right? Yes, it is. I'm going to show you a video that's from this address here. You can see this address there. It's from a TED instruction, like a TED Talk type thing, but it's a really cool thing about exponential growth with a tiny, tiny little piece of paper. So the question is, how many times would you have to fold a piece of paper to reach the moon? Okay, so if this were possible, if you could take a piece of paper and just keep folding it in half, folding it in half, folding it in half, how long until you get to the moon? That's what this little video is. The video is less than 4 minutes, okay? So don't tell me you don't have time to watch it. Come on, I see how much time kids waste in class. You got time to watch this cool thing. All right, I will see you back in the next lesson, and good luck on your mastery check.
How many times can you fold a piece of paper? Assume that one had a piece of paper that was very fine, like the kind they typically use to print the Bible. In reality, it seems like a piece of silk. To clarify these ideas, let's say you have a paper that's 1/1000th of a centimeter in thickness. That is 10 to the power of -3 centimeters, which equals 0.001 centimeters. Let's also assume that you have a big piece of paper, like a page out of the newspaper. Now, we begin to fold it in half. How many times do you think it could be folded like that? And another question. If you could fold the paper over and over as many times as you wish, say 30 times, what would you imagine the thickness of the paper would be then? Before you move on, I encourage you to actually think about a possible answer to this question. Okay, after we have folded the paper once, it is now 2/1000ths of a centimeter in thickness. If we fold it in half once again, the paper would become 4/1000ths of a centimeter. With every fold we make, the paper doubles in thickness. And if we continue to fold it again and again, always in half, we would confront the following situation after 10 folds. 2 to the power of 10, meaning that you multiply 2 by itself 10 times, is 1,024 thousandths of a centimeter, which is a little bit over 1 centimeter. Assume we continue folding the paper in half. What would happen then? If we fold it 17 times, we'll get a thickness of 2 to the power of 17, which is 131 centimeters, and that equals just over 4 feet. If we were able to fold it 25 times, then we would get 2 to the power 25, which is 33,554 centimeters, just over 1,100 feet. That would make it almost as tall as the Empire State Building. It's worthwhile to stop here and reflect for a moment. Folding a paper in half, even a paper as fine as that of the Bible, 25 times would give us a paper almost a quarter of a mile. What do we learn? This type of growth is called exponential growth. And as you see, just by folding a paper, we can go very far, but very fast too. Summarizing, if you fold a paper 25 times, the thickness is almost a quarter of a mile. 30 times, the thickness reaches 6.5 miles, which is about the average height that planes fly. 40 times, the thickness is nearly 7,000 miles, or the average GPS satellite's orbit. 48 times, the thickness is way over 1 million miles. Now, if you think that the distance between the Earth and the Moon is less than 250,000 miles, then, starting with a piece of Bible paper and folding it 45 times, we get to the Moon. And if we double it one more time, we get back to Earth.